All right, so let's jump right in. Back in the early 2000s, Google was facing a problem that really the world had never seen before. They were dealing with this absolute explosion of data from crawling the entire web. And to handle it, they didn't just need more storage. They needed a completely new way of thinking about storage. This is the story of the Google File System, or GFS, a truly legendary piece of engineering that was built for a world of constant failure.
First, let's just try to wrap our heads around the scale here. We are talking about managing hundreds of terabytes of data, and that data was spread across thousands of disks on over 1,000 different machines. And remember, this was growing every single day. The challenge wasn't just storing it, but being able to get to it quickly and reliably all the time.
And here's the real kicker. They decided to build this absolutely colossal system not on expensive, super reliable mainframes, but on thousands of cheap, off-the-shelf commodity servers. You know, the kind of hardware that was pretty much guaranteed to fail. We're talking application bugs, disk failures, bad memory, network outages, you name it. They didn't just plan for it, they expected it to be happening constantly.
So when you're facing a problem this unique, you just can't use the old rulebook. It won't work. So the GFS engineers, well, they basically threw it out. They started from scratch, looking at their specific needs, and that led them to a radically new philosophy for building a file system.
This single sentence from their 2003 paper is the key to understanding everything about GFS. This wasn't a bug they were trying to fix, it was a fundamental law of their universe. So instead of trying to prevent failure, they decided to embrace it. They designed a system that just assumed it was constantly in a state of partial failure and needed to be able to heal itself, automatically.
And this really highlights that huge paradigm shift. You see, traditional systems were built assuming hardware was reliable. GFS assumed it would fail. Old systems were optimized for tons of small files, but Google had a smaller number of absolutely enormous multi-gigabyte files. They didn't really need super low latency for one-off operations. What they needed was massive, sustained bandwidth to stream through huge data sets. And finally, their applications rarely overwrote data. They almost always just appended new data to the end of a file.
So, with that totally new philosophy in mind, what did the actual blueprint look like? Well, maybe the best way to think about it is like a giant library, but a library designed by an engineer who fully expects the bookshelves to just randomly collapse all the time.
The architecture basically has three core parts. First, you've got a single master server. This is our librarian. It manages all the metadata, think of it as the card catalog, but it never ever touches the actual books. Then you have thousands of chunk servers. These are the bookshelves, the workhorses that are actually storing all the data. And finally, you have the client, which is just the application that's trying to read or write a file.
Now, in GFS, files aren't stored as one single thing. They're broken up into these big fixed-size pieces called chunks, and each one is a whopping 64 megabytes. Now, that large size is a really critical design choice. It means a client who's reading, say, a gigabyte file only has to talk to the master a handful of times, which dramatically reduces the master's workload.
So let's see how all these pieces work together. When a client wants to read a file, it first goes to the master, our librarian, and asks, hey, where can I find chunk number 5 of this file? The master just looks in its memory and replies with the addresses of the chunk servers holding that piece of data. Then, and this is so important, the client goes directly to one of those chunk servers to get the data.
The master is never part of the data transfer itself. It only handles those little metadata requests. This separation of the control flow from the data flow is really the secret sauce here. It's what prevents that single master server from ever becoming a bottleneck, which is what allows the entire system to scale out to thousands of machines and petabytes of data. It's just brilliant. Okay, so we've got the architecture down, but what happens when one of those thousands of cheap bookshelves, inevitably collapses? This brings us right back to that core philosophy, designing for failure. Let's take a look at the GFS safety net. The first and honestly the most important layer of that safety net is replication. By default, GFS doesn't just store one copy of your data chunk. No way. It stores 3 copies on 3 completely different machines.
And it's even smarter than just picking 3 random machines. GFS actively places those 3 replicas on different server racks. Now, why does that matter? Well, because it means the system can survive not just a disk or a machine failure, but an entire rack going offline because of something like a bad network switch or a power failure. They thought bigger. The whole safety net is really multi-layered. Beyond just replicating chunks, the master is constantly checking in on every single chunk server with these little heartbeat messages.
If a server stops responding, the master just assumes it's dead and immediately kicks off an automatic recovery, cloning that server's data onto other healthy machines. And finally, to guard against that sneaky silent data corruption, every chunk has a checksum to make sure the bits haven't flipped.
So how fast is this self-healing process? Well, in one experiment they talked about in the paper, the team intentionally killed a chunk server that was holding 600 gigabytes of data. The GFS master detected the failure and restored all of that data, creating brand new replicas across the cluster in just over 23 minutes. The system just fixed itself. No pagers went off, no one had to intervene.
So we know the design is brilliant and incredibly resilient, but how did it actually perform out in the real world? And what was its ultimate impact?
One of the really unique features this design made possible was something they called atomic record append. It's a special kind of write operation that let hundreds of different programs add data to the same file at the same time without messing each other up. GFS guaranteed that each append would be written perfectly as a single atomic unit. This was an absolute game changer for the massive producer-consumer systems Google is building.
And this is a snapshot of a real live production cluster from the paper. You can just see the scale. 227 servers, 18 terabytes of disk space. But look at that last line. The master, the single brain of this entire gigantic operation, needed only 60 megabytes of memory to manage all of it. That is just an insane level of efficiency.
The performance numbers also totally confirmed their design goals. For this one cluster, the sustained read rate was a massive 589 megabytes per second. Now, the write rate was a lot lower, but that was completely expected. In fact, it was fine, because they had correctly assumed from the start that their workloads were going to be dominated by these huge streaming reads.
You know, the impact of GFS goes so far beyond just Google. Its core ideas, breaking files into large chunks, replicating them across cheap machines, and managing it all with the central master, that became the direct inspiration for the Hadoop Distributed File System, or HDFS. And HDFS, in turn, basically powered the entire big data revolution for the next decade.
Ultimately, the GFS paper left the world with this incredibly powerful and really counterintuitive idea. It proved that by embracing failure as a constant, as the norm instead of the exception, you could build systems at a scale and a level of reliability that were just unimaginable before. So it kind of leaves us with this provocative question. What if the best way to build a reliable system is to assume it's always broken?